Welcome everyone to today's webinar on simulating manufacturing processes with MSC Software Solutions. My name is Srinivas Reddy and I'm Product Marketing Manager at MSC. During the presentation, if you have any questions, please post them in the Q&A panel and we'll get to them once the presentation is done. So with that, let me go ahead and get started. So simulation, of course, is very widely used for virtual product testing to analyze behavior of the products, and the products may already be in service, or they could be a new concept that you want to test. And manufacturing complements the product development by turning ideas into reality. You could have a design that works on paper, but how you create the product is very important as well, as the process itself could affect the performance of the product. So in this webinar, we will focus on how simulation and specifically a Marc solver from MSC can help simulate these various manufacturing processes and how you can benefit from that. So I'll go a quick review of manufacturing processes, and after that we'll see how simulation can help and why technology of Marc provides an excellent solution. This will be followed by a demo, and then after summarizing we will go into the Q&A. Manufacturing can be defined as any process that transforms raw materials into a new product, and this new product from one process can be a raw product from another for a different one. So the final product that a consumer gets to use could actually have gone through several of these processes, and these manufacturing processes can be classified into 5 major groups. The first one is forming, and the forming processes are used to change the size and shape of the industrial stock, and pressure is normally employed to squeeze or shape the material, and generally there is no loss of weight or volume of the workpiece during this process. And the type of process used depends on the material, whether it is a metal or non-metals like polymers or composites or ceramics, and it also depends on the final shape that we're trying to obtain, and finally the cost of the process itself. And the next one is separating processes, which are used to remove material or volume, processes like milling, cutting, grinding, drilling, etc. The next class is fabricating processes, which are used to join or fasten the materials, and things like mechanical joining, cohesion, they fall into this category, like soldering, welding, riveting. Are some of the examples. The next one is the conditioning processes, which are used to change the internal or external properties of the materials, and this could involve using heat, chemical, or mechanical means to change the structural characteristics of the material. And they're used to change properties like hardness, the strength of the material, resistance to wear, and even fatigue life of the material. And finally, the finishing processes are used to improve the outward appearance or to protect the exterior surface. Processes like smoothing, polishing, and even painting, they fall under this category. There are various challenges involved in deciding on the process that is used to making a part, and to start with, one needs to understand the nonlinear behavior of the material that is being formed or being worked on. And at higher temperatures, the time and temperature dependent responses become much more prominent, and they play a role in residual stresses in the final part. And you should also be concerned about the various parameters, because while a faster manufacturing process can help turn out more parts in less time, if the parameters are inappropriate, it can lead to increased failure during the manufacturing process or in the service. For example, if a sheet component could turn out to be thinner, and there could be higher stresses, and that could lead to early failure. Slow ones, on the other hand, can be economically non-viable because it just takes too long to make each part, and it won't be profitable for the manufacturer. And since there would be some form of spring back in most of the cases, we also need a way to measure and design a process to control the amount of spring back. Otherwise, the part you get may not have the exact shape that you require. And finally, you would also need to consider the possibilities of damage buildup and the failure that can occur either during the manufacturing process or in service. And a lot of times, manufacturing simulation is concerned with figuring out just the material flow, not all the aspects that were mentioned here. But as you see, there are a lot more issues that we need to understand to come up with optimal parameters and deciding on the appropriate process. And in addition to the ones that I mentioned earlier, like tool wear also plays a very key role in deciding on the quality of the final product, because as the tools wear, it can lead to deviation from the desired product tolerances and the process parameters that are optimal. So because of all these issues involved, it is definitely not prudent to rely solely on empirical data to design a better process. Now, let us see why Marc is a great solution for the simulation of manufacturing processes. In fact, this is probably the only solution that is available to address not only your product testing and analysis needs, but also to simulate the manufacturing processes like forming, cutting, welding, annealing, and so on. Marc does offer a wide range of plastic material formulations to simulate the response of metals and non-metals alike. It supports isotropic, kinematic, and combined work hardening, and also numerous yield criteria ranging from von Mises to anisotropic Hill criterion, Barla model, exponential cap, just to name a few. And viscoplasticity formulations are also supported for temperature-dependent response. And finally, users also have the ability to create their own customized formulations with the help of user subroutines for any special classes of materials. And the damage and failure models are available in Marc, which are crucial because we need to ensure that the product that is being made would not fail during the manufacturing process. And there are several damage indicators that are defined based on plastic strain, stress, and temperature or other state variables. And next, you would see wear. Wear is an important physical phenomenon in any structure that is subjected to repeated loadings. And by wear, we actually mean the loss of material from the surface. And this loss could be either due to mechanical or chemical processes. And since tools undergo repeated loading, they experience gradual wear. That needs to be understood so that you know when the tools themselves need to be replaced so that the rejection rate of your products is not high. And with Marc, you can compute the progression of wear based on Archer's equation, and which is defined as a function of temperature, normal stress, and the relative velocity between the two contact bodies that are in contact. And the next one, as many of you may be aware of Marc's robust contact capabilities, and they provide excellent advantage in setting up these types of problems here. And the third one, you see the remeshing capabilities, and which can be local or global. In the case of local remeshing, elements are subdivided into smaller elements based on specific criteria like stresses or being in a specific contact area and so on. And this helps with getting improved accuracy in the areas of high gradients. And the next one is the global remeshing, and it is shown in the example here at the bottom. It is used to replace the entire existing mesh of a contact body. And there are two approaches to global remeshing. It could be either local or it could be manual or automatic. And especially with the automatic one, the effort on your part is much less. Whenever certain elements exceed the distortion, and if there are some convergence problems, Marc would automatically replace with a new mesh. And there are several high-performance computing capabilities, and one of them is parallel processing, and including the support for GPU, so that you can take full advantage of the system resources that you have at your disposal. And Marc's capabilities are very well suited to simulate a large number of manufacturing processes, including various types of forming, cutting, material removal, riveting, welding, and so on. And also, due to the implicit methodology that is used in Marc, the spring back calculations especially are much more accurate compared to some explicit solutions that are available for this class of problems. So let me go over a few examples where Marc is used to solve and simulate. The first one is sheet forming. There you see a rigid die, and also there is a worksheet that is deformed using pressure. And you can see that extensive amount of contact that takes place as it deforms, and also there is a very large amount of deformation. So the goal, of course, is to find out, to make sure that this does not thin extensively, and also the sheet does not wrinkle while during this operation. The second one involves cutting or the material removal, and there is once again large amount of distortion, and the remeshing definitely helps quite a bit in this type of problems. The third one you see is crimping of wires. Multiple wires are compressed in this case, and as they undergo distortion, not sure if you see very clearly, but it actually undergoes remeshing. So each of them is undergoing separate remeshing over there, and there's a very large plastic strain as well. And next you see the extrusion problem, and there's also damage contours that are being shown here. And other one, you see the tube bending. Once again, you see the plastic strains, and also there is a large amount of deformation. And finally, there you have twisting of the cables. This again, large deformation, and even the contact. Since we don't use the contact pairs, but rather the contact body definition, it is quite easy to define the contact for these types of problems. So today I'm going to show how to perform the superplastic forming simulation using Marc. So that is the example I'm going to use. And some of you may be aware that superplasticity is the ability of a material to undergo very large deformations with strains sometimes exceeding 1000% without necking. And this property is found in several metals and alloys, and especially in titanium and aluminum alloys. And that's the reason, actually, since these materials are used in automotive and aerospace industry, this process, this forming, is used quite a bit in both these industries. And superplasticity is found to coincide with fine grain size, deformation temperatures that are greater than 0.4 times the melting point, and also the strain rate sensitivity factor that is greater than 0.3. And as shown in the equation here on the right, you see that the yield stress is a function of the strain rate. So we need to get the material parameters of the coefficient and the exponent that define the particular material. And often the temperature is constant, but if the temperature changes, we need that information as well during the process. Often the elastic region is ignored, since it is performed at higher temperatures. There is very little elasticity, so that part is ignored. So models generally, these materials are generally modeled using rigid plastic material model. So I'm going to show an example and show you how to create this type of model, how to perform this type of analysis. And it is a simple model in the sense of geometry. So I have a 3D die that is defined the surfaces, and we have a sheet. And so there are two contact bodies. And I'm going to define the material properties and define the boundary conditions and so on. So let me switch to Mentat, which of course is the modeler or pre and post processor for Marc. So here, once I already have the mesh created, so that I don't have to go through that step at this point. And these surfaces, we have a bunch of surfaces and the mesh. You see all the elements at the top. And these are defined as membrane elements. And the membrane elements, they do have certain thickness, which is, here I already defined that, which is 0.08 inches. And next, I'm going to go ahead and create some material properties. So going over to new standard, and I'm going to create the material properties, input them. As I mentioned earlier, this is going to be a rigid plastic material, and with the plasticity properties, and I'm going to use power law. And you see the coefficient here, these are the properties I'm going to use for this material. And let me save the properties. And I'm going to apply this to all the elements, so which is all existing in this icon here. So now we have defined the material properties over here. And the next one, we can define the contact bodies. So there are two contact bodies. So the first one is, I'm going to define this workpiece. So they all belong to one contact body. So all the elements, and we have a body defined. And the next one is a rigid body. So I'm going to use the geometry. So since the rigid bodies don't experience any kind of stresses, we are not interested in the stress buildup in the rigid bodies. We don't really need to mesh them. So I'm going to use the surfaces that are defined. And so I have the surfaces. Once again, all these surfaces belong to this rigid body. Let me show identify so that you can see those two contact bodies. So the first one is the finite element mesh, the second one is the surface, and we have the two contact bodies. And there is one thing I want to point out here. You see that there is a gap between those two, and we do want to apply pressure on the top, so it is best if we close that gap. But again, if you want, you can try to measure the gap and close it, but another easier way is to actually specify. There is something called the approach velocity, and that essentially works as a vector. So you are specifying that you want to move it in the y direction, so move the rigid body in the y direction, so that any gap is closed. So at the very beginning, before the start of the stress analysis, the gap is closed with that. So we have the contact bodies defined, and then next we can define the boundary conditions. There are two types of boundary conditions. One is the displacement boundary conditions to apply certain fixed displacements, and the second one is applying pressure to deform the sheet. The first one, let me name it, I say fix, and I'm going to fix all the nodes and that are around, that are on the exterior. And right now in this model, they're not associated with any curve. Otherwise, I could have selected the curve, but since they're not associated, they're not attached to any curve, I'm going to use slightly different method to make it easier, which is under selection control. And I'm going to, for the method, I use edge flood. So I select nodes because we want to apply the boundary condition on the nodes, and I select an edge that is on the exterior, and you see that all the nodes on the exterior are selected, and I can come here and say nodes, and these are, I want to apply the boundary condition to all these selected nodes. So you see that we have a fixed boundary condition on the exterior. And let's clear that, and now let's create a new boundary condition, which is, I'm going to fix it in the x direction because it is symmetric, and see that I want to apply the boundary condition along the nodes along this particular line. So I'm going to follow the same approach, the nodes, and select an edge, and you get all the nodes picked, and nodes add selected. And so the next part is my other boundary condition. I go over here, fix the z direction, and nodes add, and I select an edge on the outer. So once again, we have all the nodes and all selected. So you can see that now if I want, I can verify the boundary conditions, all these fixed boundary conditions that are there. At this point, we have all the displacement boundary conditions. There is one more boundary condition, very important one, which is the pressure. We want to apply pressure on the sheet. So for that, I'm going to select faces, all the faces here, and you see that. So we have all the faces selected. It is showing up here, but you don't see the arrows yet because I have not specified any specific value over here. And once I go into properties, I'm going to use superplasticity control. The default is entered values where you specify a certain pressure. And in superplasticity control, I specify pressure. You notice that the arrows are going up. Actually, the way it is, it's going to push the die away, the worksheet away from the die. So instead, I'm going to change the pressure direction. So it is negative. And so now it is pushing downward the way we want it. Notice that I did not specify any value, any particular pressure value here. And the reason for that is in superplastic forming, the goal is to actually identify the amount of pressure and the how you want to vary the pressure with time. So that is the goal of the SPF analysis. And that's why I don't have any pressure value, because that is actually going to be output. But we do want to specify where the pressure is going to be applied. So we have the boundary conditions, and so all the basics are set up, or they're done. Now the only thing left is to create the load cases. And I go to static and go on to properties. And by default, all the boundary conditions that we created are selected. And in this case, we do want everything to be applied. So I don't need to change anything over here. And the only other thing here in this list is the superplasticity control. You would go in there, and there are a few values that we need to enter. The first one is the minimum pressure. Minimum is how much you want to apply. What is the minimum amount of pressure you want to apply to deform this? So I just give a small number. And the other is what is the maximum amount of pressure you want to apply. So I have 300. We could have even smaller or bigger. And again, that value we choose depends on the thickness of the material and the material itself, the material properties, and so on. And I give 300 is a bit higher value, but that is fine because that just serves as an upper limit. It won't apply any pressure higher than 300. So that's the idea there. And the superplasticity behavior itself, it exists only in a certain narrow range of strain rates. So we want to restrict to that range. Once again, that is a material property that you typically know. For this one, the value is 0.0002, and I entered. So I want to maintain as close to that as possible as we apply the loads. So we don't want to apply loads such that the strain rate strays too far away from this number. And this one you can leave it as default. Notice that, remember that where I was using the membrane elements. That is what I have, all these. And with membrane elements, they do not have bending stiffness. So we do need to apply some kind of initial stress so that the whole system, the whole model is not unstable. So we apply initially some certain pre-stress, which is then removed gradually so that it doesn't affect the results. So it is only for the initial increments. And finally, there is an option called fraction of nodes in contact. What this does is once all these nodes are in contact, which is 1 means 100%, once all the nodes that are here are in contact, we know that the analysis is complete. And so this is slightly different from where we generally apply the total amount of load or total amount of displacement. And in this case, we still need to figure out what that load is. So that is why we can't say once you apply some 100 psi or 300 psi, say that it is done, because that is not what our goal is. Our goal is to find out what that load is. And the completion criterion is to make sure that all these nodes are in contact. Remember that there is no spring back in this type of analysis. There is no elasticity. So we don't need to worry about the node that is in contact springing back because of elasticity. So we have the load case defined, and since this is a rate dependent material, time is not a dummy time. This is real time. And I am specifying 7200. It means that once again it is a maximum value, so it runs, the process doesn't run more than 2 hours, so the physical process. And we do expect the whole forming operation to complete before 2 hours. So that's why we specify that number. And finally, with this multi-criteria, the adaptive stepping criterion. There's only one thing. I want to start a bit slow for these types of problems because, again, these are membrane elements, and initially there could be some kind of instability. So I want to apply the loads slowly and ramp up. As the solution converges, the Marc itself would automatically increase the load. So we have all the things that are needed to define the load case. So that is set up. So the key thing is that superplasticity control. That is the thing we need to define in addition here. And I go to jobs, and here where there is not a whole lot of difference in what we do in a typical analysis. To make sure I select the load case and my initial loads. This is what I want. I want to fix all the boundary conditions and analysis options. This is definitely a large strain problem. And the results. We want to select a few results, result quantities. One misses stress and no elastic strain, because there we expect that to be 0. And there is plastic strain. We can look at plastic strain rate as well. And another important thing is thickness. We want to make sure it does not thin too much. So we want to measure that as well. So thickness of the element. So those are all the things that are needed here. So we have everything set up for the model, and we are ready to run this. And as you see that I have already run this model, and notice that we specified a total of 7,200 seconds to run the process, but the job actually completed within 4,680 seconds. And that because here the completion criterion is all the nodes are in contact. So that's the idea. So since all the nodes are in contact at this time, the job is considered to be complete. So let me open the results file, and I will show a few quantities. Let me show the thickness distribution so that you can see how the thickness varies. And let me play this. So you see how it deforms. We started off with 0.08, and you can see the variation. It's over here that in the center that you see the most thinning, as you can expect. And notice is that in this curved area, we could have used a finer mesh. And since this analysis does run quickly, we could have gone for even finer mesh, or we could have also used adaptive meshing, which could be local adaptive or global. We could have used either of those here. Let me show a couple of more things. One is the path plot. Let me go back to the first increment, and let me show one thing. So let me show the node path. I'm going to select these two nodes because I want to select everything in between and add curves. I need to add curve, and the length from the center versus the thickness. We want to see how the thickness varies. And I'm going to do one more thing. So minimum is about 0.03 inches, actually slightly higher than that. And the maximum is 0.08 because that was the original thickness of the plate. So we know that it is going to change only in between those. And let me play or monitor the results. You see that with each increment, as the increment is changing, you see how the thickness along that path is varying. So closer to that fixed boundary condition, you see that it is there's a little bit less thinning, but in the center, you see a lot more thinning. You see which areas you see a lot more thinning and a lot more variation when it is going over the curve. So that's what you're seeing here. And so you can choose any kind of path, any arbitrary path. You can choose, although I chose nodes, you could create some points and nodes by yourself, and you can use that to define or to plot variation of not just the thickness, but even the plastic strain or any other result quantity that you have saved. And finally, I'm going to show one more thing in the history plot. Remember, I was mentioning that pressure variation is one thing that we are interested in this SPF or the superplastic forming analysis. So let me go ahead and get the information, and I want to add curve. This is the global information and time versus the process pressure. And let me fit this. So here you see we are starting at time 0, where the pressure is 0 and the pressure is gradually increased. You see that towards the end it has a spike up, and it's mainly because that bottom corner, that is where it is trying to fill the area in that region. So they had to apply higher pressure. So that is why, like you see, certain variation or gradually it is increasing over in the last few increments. So most of the time, actually, it is only it's less than half of this 56. So the 56 is the maximum pressure that is needed to form this part. So this concludes the demo part. Let me go ahead and go back to my PowerPoint slide and quickly summarize and move on to the Q&A. So we have seen how we can use Marc for various manufacturing processes, and because of its capabilities and ease of use for in contact and also in nonlinear materials, and the special capabilities for some forming operations, some manufacturing applications, it is an excellent solution for these problems. And you can definitely find a lot more examples in the Marc documentation and with detailed step-by-step procedures. And if, again, I did not cover every single process, every single manufacturing process that could be handled by Marc, but if you have any specific process in mind, you can definitely send me an email, and I can get more information on that to you, and or point to the documentation in Marc's manuals. Let me move on. Thank you very much.